Hello everyone, welcome to Chem 9. Today we will begin chapter number 5. This chapter deals with chemical quantities and it will also introduce us to chemical reactions. This chapter is divided in 3 sections. In first section we will discuss about the mole concept. In this concept we will learn how the number of atoms or molecules are related to the mass of matter. In second section, we will discuss a method to describe a chemical reaction and in form of a chemical equation. And we will learn how to write a chemical equation, and we will also learn how to balance a chemical equation. And finally, at the end, we will talk about how many different kinds of reactions are possible, and we will learn how to recognize different types of chemical reactions. A chemical reaction is a process in which a substance known as reactants undergo a change to become a new substance, and that new substance is known as products. One of the important example of a chemical reaction which saves many lives can be seen in our motor vehicles. Have you ever wondered, in case of a collision, how come the airbags get inflated in such a small amount of time? In fact, no mechanical pump is available which can inflate these airbags in a fraction of a second, which are needed in case of a collision to save lives. The airbag is inflated when a sensor at the front of the vehicle detects a sudden deceleration, such as which occurs in case of a crash. The gas which inflates these gas molecules. So this gas that inflates the bag is produced in a chemical reaction. The inflated airbag creates a cushion between the steering wheel and the driver moments before the driver's head and torso make contact with the airbag. The chemical reaction that causes an airbag to inflate is the decomposition reaction of sodium azide, which leads to the production of two products. One is sodium metal and the other one is nitrogen gas. And this nitrogen gas is the substance which inflates the airbag. These numbers in front of reactants and products are the ratios between reactants and products which will be produced or used in the chemical reaction. It is extremely important to use the exact amount of sodium azide in the airbag to make this airbag effective. If we use too little sodium azide, then it will not produce enough nitrogen, and hence airbags will not be fully inflated. However, if we use too much of sodium azide, then the explosion will be too large and the explosion from the airbag may or will hurt the passenger. So it's extremely critical for engineers to come up with the correct amount of reactants. So in this chapter, we will learn how to relate the quantity or the number of atoms or molecules with the mass of any chemical. So hence in this chapter we will introduce the principle that govern chemical reactions and the quantitative relationships they describe. Then in next chapter we will describe the energy associated with chemical reactions. In previous 3 chapters we learned about composition of matter, elements and compounds. In this chapter we will focus on chemical changes in matter. Chemical changes are also known as chemical reactions, and they are processes in which elements and compounds are transformed into new compounds or elements. In this process, existing bonds will break and new bonds are formed. For example, This schematic shows a chemical reaction between hydrogen gas molecules and oxygen gas. The green molecules represent hydrogen gas, and we know hydrogen gas is made up of two hydrogen atoms bonded together. And in this reaction, hydrogen gas is reacting with oxygen gas molecule, and we know oxygen is made up of two oxygen atoms and they are also bonded. And in this chemical reaction, the bond between hydrogen atoms will break, and also the bond between oxygen atom will also break. So this is the bond breaking step. And after the bonds are broken, two of the hydrogen atoms and one oxygen atom, so they combine to form water, which is H2O or HOH. And in water we know that a bond between hydrogen and oxygen is formed. So this is a new bond. So that's what a chemical reaction does. Existing bonds break and new bonds are formed. Similarly, the remaining two hydrogen atom and the remaining oxygen atom also creates new bond to form the second water molecule. So this process describes what happens in a chemical change. In a chemical reaction, atoms, ions, or molecules combine in a whole number proportion. For example, the reaction of sodium azide in case of airbags uh, can be described as this equation. So in this reaction, this number 2 represents that there are two molecules of sodium azide react to form two molecules of sodium and three molecules of nitrogen. So in other words, these number of molecules which participate and formed in the reaction are in whole number proportion. So what I mean with that is that it's never going to be fraction. It's never going to be that 1.5 molecule of this sodium azide produce 3.2 molecules. So that's never going to happen. So fractions of molecules do not participate in the reaction. It's always going to be a whole number. Engineers rely on this concept to calculate the amount of gas that will be produced in a chemical reaction, such that it inflates the airbag properly. In other words, the amount of nitrogen gas which is produced in this reaction is critical so that the airbags do not underinflate or overinflate. Similarly, when a nurse administers a dosage of medication to a patient, they need to be certain that the correct number of atoms, molecules, or ions are given to the patient. For example, an IV solution of physiological saline administered to a patient must contain the proper number of sodium and chloride ions. Otherwise, consequence can be disastrous. So if the number of molecules, such as the number of nitrogen molecules or number of sodium chloride molecules in case of a patient, are so important, now the question is, how can we count them? In chapter number 2, we learned that atoms and molecules are extremely small. We can't even see them. So if we can't even see these molecules or atoms, how can we count them? Now, since the atomic mass of a single atom is known from the periodic table, we can calculate the mass of a molecule. For example, water contains two hydrogens and one oxygen atom. So we know that the mass of one hydrogen is 1.008, and this number we got from periodic table. Similarly, we know the mass or atomic mass of one oxygen atom, which is 16.00. So with this knowledge, we can add all these masses up and we can calculate the total mass of water molecule. So knowing the mass of a single atom or molecule, it allows us to calculate the mass of a large number of atoms, molecules, or even formula units. Hence, there is a quantitative relationship between the number of particles in a sample and its mass. The number of particles in a macroscopic sample can therefore be obtained by weighing. In chapter number 2, we learned about the atomic mass. Now, atomic masses value appear in a periodic table. So, for example, hydrogen atom, which is present here, it has atomic number 1 and its atomic mass is given right underneath. And if you look carefully in any periodic table, you will find that the mass of hydrogen atom is 1.008. So this number is the atomic mass. So atomic mass is the mass of any atom in AMU scale. It's not in grams, it's in AMU. AMU stands for atomic mass unit. So in other words, atomic masses can be found in periodic table. So if the atomic masses are known, we can calculate the molecular mass. Mass of a molecule is known as molecular mass. For example, if I have a carbon dioxide molecule and I would like to know what will be its mass. So mass of the entire molecule is known as molecular mass. Now, carbon dioxide molecule is made up of one carbon and two oxygen atoms. So if I want to figure out the mass of a carbon dioxide molecule, I need to know the mass of carbon as well as mass of oxygen. If we look carefully in the periodic table, we'll find that carbon atom has a mass of 12.01 AMU and oxygen atom has a mass of 16.00. Now because we have two oxygen atoms and one carbon, so therefore total mass in CO2 will be carbon mass or carbon atomic mass plus 2 times oxygen atomic mass. So it will come out to be 12.01 AMU plus 2 times 16.00 AMU. And if we add all these masses up, it will come out to be 44.01 AMU. So this will be the molecular mass of carbon dioxide. By applying the same concept, we can calculate molecular mass of any other molecule. For example, we can also calculate the mass of water molecule. Now, water molecule is made up of two hydrogen atoms and one oxygen atom. And we know that each oxygen atom weighs 16.00 mu, or in other words, atomic mass of oxygen is 16 and atomic mass of hydrogen is 1.008. So as we have two atoms of hydrogen, so combined mass from hydrogen atoms will be 2.016 and the mass from oxygen atom is 16, and if we add them up and round it off to correct sig figs, the mass of water molecule will be 18.02 AMU per molecule. In other words, each molecule of water will have a molecular mass of 18.02 AMU. Let's calculate mass of a glucose molecule. In glucose molecule, we have 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. So in order to calculate the molecular mass of glucose, we need to know the atomic masses of carbon, hydrogen, as well as oxygen. Because we have 6 carbon atoms, therefore 6 times the atomic mass of carbons will come out to be 72.06 AMU. We have 12 hydrogen atoms, so 12 hydrogen atoms. Each hydrogen atom is 1.008. So if we multiply 1.008 with 12, we'll get 12.096 AMU. And glucose has 6 oxygen atoms, and each oxygen atom has a atomic mass of 16.00 AMU. So 6 of them will have combined atomic mass of 96 AMU. So by combining all the masses together, we can calculate the molecular mass of glucose. So that will be equal to 180.16 AMU. If we have a sample of matter such as a gold jewelry or iron rod, it will be composed of enormous amounts of atoms or molecules. So when we count large number of objects or particles or any other thing, we use counting units. For example, if I have 12 coins, the unit I can use is dozen. So 12 is dozen. So 12 coins, I can say I have 1 dozen coins. So 12 is, or dozen is a number unit. It represents 12, number 12. Similarly, when we have large number of paper sheets such as given here, so the number or the unit we use is ream. 1 ream is equals to 500 sheets. So instead of saying that we have 500 sheets, you can say 1 ream. So for example, I have 4 of these reams, so it means in each I have 500 sheets, so together I have 2000 sheets here. So ream is a unit to calculate or to represent a number of sheets. In this case is 500 sheets. Similarly, when we count atoms or molecules, we or chemists, they use a unit or counting unit, and that counting unit is known as mole. It is also abbreviated as MOL, not much of an abbreviation, but many times we use just MOL. So 1 mole is an extremely high number. It is a really large number, much greater than a trillion. So 1 mole is equals to 6.02 times 10 to the 23 numbers. This number is also known as Avogadro's number because it's named after the scientist who brought this number up. So this is also known as Avogadro's number or Avogadro's constant. Avogadro's number is defined as the number of carbon atoms present in 12 grams of carbon sample. So Avogadro's number is based on the number of atoms present in 12 grams sample. So what does that mean? So it means is that imagine that you weigh pure carbon. So imagine this is a weighing balance and you weigh a sample of pure carbon. So pure carbon is like graphite. So imagine this is the black powder represents pure carbon. And if you weigh 12.00 grams of pure carbon, so 12.00 grams of pure carbon, So in this sample, if you count all the atoms present in 12.0 grams of sample, so that atoms will be equal to 6.02 times 10 to the 23 atoms. So in other words, 12.00 grams of carbon will contain 1 mole of atoms, because this number is also known as 1 mole. So in other words, Avogadro's number of particles is equals to 1 mole of those particles. And now we can extend this definition beyond carbon. It is so for example, if I say I have 1 mole of helium, what I'm saying is I have 6.02 times 10 to the 23 atoms of helium. If I say I have 1 mole of glucose molecules, what I mean is that I have 6.02 times 10 to the 23 molecule. So 1 mole is also known as dozen for chemists, because just like dozen is just a number, so you may have 1 dozen eggs, 1 dozen bananas, 1 dozen oranges. All it means is that you have 12 eggs or 12 bananas or 12 oranges. Similarly, you may have 1 mole of any atom. All it means is that 1 mole of that atom is equals to 6.02 times 10 to the 23 of those atoms. So Avogadro's number serve as a conversion factor between 1 mole and the number of any kind of particles. Therefore, we can use this Avogadro's number as a conversion factor. For example, if we are converting mole of atoms to number of atoms, we can say 1 mole of atoms equals 6.02 times 10 to the 23 atoms. 1 mole of iron similarly will be equals to 6.02 times 10 to the 23 ions. And 1 mole, so the thing is that 1 mole is always going to be equals to 6.02 times 10 to the 23. So if it's molecules, that will be molecules. If it's formula unit, that will be formula unit. You can technically also say 1 mole of dollars is equals to 6.02 times 10 to the 23 dollars. I mean, it's correct to say. So using the conversion factor from the mole concept, we can convert the number of particles to moles or moles to number of particles. So either one of these two conversion factors will be used. So either it's going to be 1 mole over 6.02 10 to the 23 particle or vice versa. Let's take an example of a problem in which we use this mole concept to calculate the number of particles. So you may see a problem something like that. How many chloride ions are present in 0.102 moles of chloride ions? So in this case, we are given with moles. So we have how many moles? We are given with 0.102 moles of chloride ions. Okay, and we know that 1 mole chloride ion is equals to 6.02 times 10 to the 23 chloride ions. So that we know, right? Let me clean this up a little bit more. So 1 mole chloride ions is equals to 6.02 times 10 to the 23 chloride ions. 1 mole equals 6.02, or Avogadro's number. So from this equation or from this relationship, we can write two conversion factors. So one conversion factor is in which we have left hand side on top 1 mole chloride ion divided by, I'm gonna skip the word ion, it's understood, 6.02 times 10 to the 23 chloride ions. Or the second is in which we write the 6.02 times 10 to the 23 ion on top and 1 mole at the bottom. So In other words, either it's going to be left hand side over right or right over left. So this is a simple dimensional analysis trick. So now we are given with moles, and what do we want to find? We want to find the number of chloride ions. That's what we want to find. So it means we want to go from moles to number, right? So let's plug in the value. So we're gonna need a conversion factor in the middle. So you start with your starting value or given value 0.102 mole of chloride ions. Now we're gonna need to multiply with a conversion factor. Now which conversion factor we're gonna use? We're gonna use the one where the mole gets cancelled. So it means we have mole up here, so now we're gonna need mole down here so that we can cancel it, or mole of chloride. So which one has mole of chloride down in the bottom or denominator? So the correct choice is this one. So we're gonna use this conversion factor here. So it means the conversion factor will be 6.02 times 10 to the 23 chloride ions divided by 1 mole chloride ions. So now mole chloride cancels with mole chloride, and we are left with the rest of the equation. So 0.102 multiplied by 6.02 times 10 to the 23, and nothing in the denominator. That's just 1, and we have chloride ions, right? So if we solve this, the answer will be 6.14 times 10 to the 22 chloride ions. So it means we have this many chloride ions in 0.102 moles of chloride ion. Let's solve another problem. In this problem, we are given with these many formula units of sodium chloride. Formula units means that many sodium chloride molecules, and we want to find, first of all, how many moles of NaCl are present in that one spoon of NaCl. So that much simple. Remember, the conversion factor will always be the same. So 1 mole of anything, so in this case that is NaCl, is equals 6.02 times 10 to the 23 units of NaCl, sorry. So that's always going to be the same. So from this we can always gonna write the same two conversion factors. So left side over right side, or the right hand side over left hand side. So one of them we will use. So now let's start with what's given to us. So given to us is the number. So number is given and we want to find moles. So what's the number given to us? 5.15 times 10 to the 23. Formula units are just the NaCl molecules. Okay, and we want to find the moles of NaCl, right? So in other words, in this problem we want to go from number of NaCl to moles of NaCl, and of course we're gonna need a conversion factor. So one of these two conversion factors will be used. We'll see which one it's gonna work. So let's plug in the value. So how many numbers are given? So given number is 5.15 times 10 to the 23 NaCl. That many NaCl formula units are present. So what's going to be needed in the conversion factor in the denominator? Whatever cancels here. So we have number on the top, so it means we're going to need the number down here. So the correct conversion factor will be this one, because we're going to need moles on top. So it will be 6.02 times 10 to the 23 NaCl formula units, and on top will be 1 mole NaCl formula unit. So number cancels with number. Okay. This is 23. So leftover is, if we solve it, it's going to be 5.15 times 10 to the, excuse me, this is 22. So this should also be 22. So 22 here. Multiplied by 1 mole NaCl divided by 6.02 times 10 to the 23. So if we solve this, this will come out to be 0.0855 moles of NaCl. So that will be the answer for part A. Now in part B and C, we want to find out how many moles of sodium ions does this correspond to and how many moles of chloride ion does this correspond to. Now this is a qualitative kind of approach here. So let me explain. So if we have only one NaCl, and in one NaCl, if we think about it, one NaCl has one sodium ion and one Cl ion, because that's what it is. So one sodium ion and one Cl ion. So if we have 100 NaCl units, so 100 NaCl will have 100 Na ions and 100 Cl ions, right? So similarly, if you apply the same logic, if you have I don't know, 5 million NaCl, they will have 5 million sodium ions and 5 million chloride ions. So what's the point here? The point is, whatever number of sodium chloride units you have, same number of sodium ions will be there and same number of chloride ions will be there. So now in part A, we know that we have 0.0855 moles of NaCl. So what does that corresponds to for sodium ions? Whatever we have here, same number of sodium ions. So 0.855 moles of NaCl will have same number, 0.0855 sodium ions, and similarly we'll have same number of chloride ions, 0.855 chloride ions, and that's the answer for part B and part C. It is obvious that we can't actually count atoms or molecules because they are too small. We can't see them. So now the question is, how do we measure 1 mole of any element or compound? The answer is that there is a quantitative relationship between number of atoms, molecules, or formula units of a substance and its mass. So we count the atoms from the mass of that particular substance. As we learned earlier, that 1 mole or Avogadro's number is defined as the total number of carbon atoms in 12.00 grams of carbon. So in other words, 6.02 times 10 to the 23 carbon atoms, because that's the Avogadro number, it means if we have that many carbon atoms, they will weigh 12.00 grams. Now this is 1 mole of carbon atoms, and 12 is the molar mass or atomic mass of carbon atom. So it means that if you have 1 mole of carbon atoms, they will weigh 12 grams. So hence, mass of 1 mole of any substance is equals to its molar mass. So because 1 mole of carbon atom is 12 grams or 12.00 grams, so hence molar mass of carbon is 12 grams, and it is found if you compare the molar mass with the atomic mass in periodic table, you'll see that the molar mass is exactly same as the atomic mass. Only difference is that atomic mass is in the units of AMU and molar mass has a unit of grams per mole. So it is easy to find the molar mass of any substance or any element as long as you have the periodic table. So for example, molar mass of helium is 4.003 grams per mole. It is same as its atomic mass, only difference is that the unit is different. Atomic mass is in unit of AMU, molar mass is same number but the unit is grams per mole. So hence we can say that molar mass of an element has the same numerical value as its atomic mass, but the units are grams per mole. The molar mass of any element can thus be found on the periodic table. So this picture shows the quantity of copper, sodium chloride. So this is copper, this one is sodium chloride or table salt, and this is water. So all of these three substances, they are weighed to be same as their molar mass. In other words, all of these three samples contain 1 mole of copper atoms or sodium chloride units or water molecules. So they all have same number of particles, however their molar masses are different. So similarly, the molar mass of a compound has same numerical value as its molecular or formula mass, but the units are grams per mole. For example, water has a molecular mass of 18.01 AMU, thus its molar mass is 18.01 grams per mole. Sodium chloride formula is NaCl, so if we add the atomic masses of sodium and Cl, we get the formula mass of sodium chloride to be 58.44 AMU. Hence, its molar mass will also be 58.44, but units will be grams per mole. In other words, molar mass is calculated same way as we calculate molecular mass, only difference is that we put the units as grams per mole. So this concept between the moles and molar mass can be used as a conversion factor to convert from moles to mass of any chemical. And interconverting between mass and moles is one of the most routine calculations performed in chemistry lab. So let me explain with the help of one example. So imagine we have a problem something like that in which you want to calculate the number of moles in 55 grams of water. So we are given with mass of a chemical. Water is a chemical, right? So we are given with the grams or mass of a compound. So mass is given. So mass of water is 55 grams, and now we want to find moles of water. So this is what we want to find. So in other words, we want to go from mass to moles, and here we can use the conversion factor, and that conversion factor comes from molar mass. So how does that work? Now water has a formula of H2O, and if we want to calculate its molar mass, remember molar mass is same as molecular mass, but the units are grams per mole. So in other words, its molar mass is 2 times water. I'm just gonna round it off, 2 hydrogen, so 2 hydrogen plus 1 oxygen, right? So I'm just gonna round it off. I'm gonna use 1 plus each oxygen is 16. So the molar mass of water is 18 grams per mole. Now what's the meaning of molar mass equals 18 grams per mole? So the meaning is 1 mole of water will weigh how many grams? 18 grams. That's the meaning. So this is the relationship which we can use as a conversion factor. So this is the left side and right side. So we can get two conversion factors from here. So one is 1 mole water divided by 18 grams, or 18 grams on top and 18 grams of water, by the way. So 18 grams of water, 1 mole water. So one of these two conversion factors will be used here. So let's see which one we need. So given value, how much mass is given? We are given with 55 grams of water, right? So multiplied by conversion factor. So now we're gonna need to use the conversion factor which has grams water in the denominator. So therefore the correct choice is this one, because that's where the grams water is in the denominator. So we're gonna use that. So it will be 18 grams water down here and 1 mole water up here. So grams water cancel, and the remaining calculation is 55 multiplied by 1 mole water divided by 18. So when we solve this one, the answer comes out to be 3.056 moles of water. So that many moles of water. So that's how we can convert grams to moles, or mass can be converted to moles, or vice versa also. Let's try another similar problem. In this case we are given with moles of copper and we want to find the mass. So given is moles of copper. How many moles are given? Moles are given. We have 0.25 mole and we want to find mass. Mass, it means we want to find grams. That is not given. Now the molar mass is already given to us. We can use this as a conversion factor. So what's the meaning of molar mass? Meaning is 1 mole copper equals 63.55 grams. That's what it means, grams per mole. This is the meaning. The meaning is 1 mole of copper will weigh 63.55 grams. So we can use this to find our conversion factor. Now in this case, moles are given and we want to find the mass, moles to mass, and of course we're going to need a conversion factor. So let's plug in the value and then we'll see which conversion factor is the right choice, left side over right or right over left. So let's plug in the value first. How many moles do we have? We have 0.25 moles of copper multiplied by now conversion factor. So we're gonna need the conversion factor where moles of copper should be down here. So it means the left hand side should be down here. So 1 mole of copper and top side will be 63.55 grams. So moles of copper cancel with moles of copper, and if we solve the remaining equation, so it will be 0.25 multiplied by 63.55 grams divided by just 1. So this comes out to be 15.89 grams. So that many grams of copper. Okay, so let's review what we have learned so far. So we have learned that the relationship between 1 mole and the number of particles is that 1 mole is equals to 6.02 times 10 to the 23 particles. Now if we are talking about 1 mole of any atoms, so it means 6.02 times 10 to the 23 atoms. If we say 1 mole of molecules, that means 6.02 times 10 to the 23 molecules, or so on. That's the number one concept which we learned in this chapter. The second concept we learn is about the molar mass. It means that molar mass is the mass of 1 mole of atoms in grams. So it means 1 mole or let me rephrase it. So mass of 1 mole of atoms or molecules is equals to its atomic or molecular mass in grams. So using these two concepts or equations to calculate conversion factors, we can convert between mass and number of particles. Let me explain with the help of an example. So for example, if we have a problem something like this, how many copper atoms are in 5 grams of copper? So what is given to us, so we have a piece of copper metal, and mass of that metal is equals to 5.0 grams of copper, right? So that much that much mass is available, and we want to find number of atoms, right? So how can we do that? So what we can do here is, we know how to convert mass to moles, because that's what we learned in previous slide, and we also know how to go from moles to number of atoms, because that's what we learned earlier. So let's uh, solve this one. So we're gonna need a conversion factor. So this conversion factor gonna come from the molar mass equation or molar mass concept, and this conversion factor, and that's gonna come from the Avogadro relationship, Avogadro number. Okay, so let's write these two equations for copper. It's gonna be the same one, but now we're gonna write specifically for copper. So we know that 1 mole copper is equals to 6.02 times 10 to the 23 copper atoms, right? So that's the relationship between mole to atoms. So we can use this to find a conversion factor, this one where we go from moles to the atoms, number of atoms. Now the second relationship which we can write is between 1 mole copper will weigh, how many grams it will weigh? Its molar mass in grams. So molar mass of copper is, as we know from the previous slide, 63.55 grams. So 1 mole of copper will weigh 63.55 grams. So that's the relationship between moles and mass, right? So this we can use to find conversion factor which relates the mass with moles. So let's plug in the values and see how we can find our answer. So how many grams are given? So we are given with 5.00 grams. So let's plug in that value. So 5.0 grams of copper multiplied by our first conversion factor. So first conversion factor is between mass and moles. So now grams are on top, so it means we're gonna need to use these grams in the denominator. So we will get 63.55 grams here and 1 mole copper up here. Now in this that's our first conversion factor. So if so grams copper will cancel with grams copper, and now we have mole of copper, so it means we are at this step. So now we need to multiply with the second conversion factor. So second conversion factor gonna come from the equation given up here in purple color. So now if you see, mole of copper is up here, so in this conversion factor mole of copper should be down here, and up here will be 6.02 times 10 to the 23 copper atoms, right? So now again mole of copper cancels with mole of copper, and if we solve the remaining equation, we will get our answer. So let's clean this equation up. So 5.00 times 1 times 6.02 times 10 to the 23 copper atoms divided by 63.55 times 1. So when we multiply everything and divide by 63.55, we will get 4.74 times 10 to the 22 copper atoms, and now we know how many atoms are there. Let's solve one more problem. In this problem, we want to find how many molecules of ibuprofen are present in 200 milligram dose. Right? So given is mass is given. It is equals to 200 milligram of ibuprofen, right? So I'm not gonna write the entire formula. It's understood. It's C12H18 and O2. But we're just gonna remember that we are talking about ibuprofen. And remember, in molar mass, all the masses are given in grams, but in this case we are given milligrams. So it's a good idea to convert milligrams to grams immediately. So I'm gonna do that. In order to convert milligrams to grams, we already have done these kind of problems many times. So we know 1 grams equals to 1000 milligrams. So this would be the conversion factor to convert from grams to milligrams. So milligram and milligram cancel, and when we solve it, it comes out to be 0.200 grams of ibuprofen. Okay, I'm just gonna call it IB. IB means ibuprofen. And what do we want to find? We want to find number of molecules. So in that small tablet, how many ibuprofen molecules are there? Right, so it sounds so tedious, but we know it's not that difficult. All we need to know is the mole concept relationship. So let's write those two relationships on the side. So we know that 1 mole of anything, in this case is ibuprofen, is equals to 6.02 times 10 to the 23 molecules. And we also know that 1 mole, let me use different color. We also know that 1 mole ibuprofen will weigh its molar mass. So let's calculate the molar mass. So we have 12 carbons, 18 hydrogens, and 2 oxygens. So 12, each carbon is 12. I'm just gonna use the whole numbers. Plus 18 times 1 plus 2 times 16. So this comes out to be, its molar mass comes out to be, let me multiply. So total it comes out to be 194 grams per mole. So this is the molar mass. So from this, what we can say is that 1 mole of ibuprofen equals 194 grams. So we can use these two relationship to find the conversion factors to go from grams to number of molecules. So we gonna go from mass to moles, and then from moles to number of molecules. We're gonna need a conversion factor, and that conversion factor be between mass and moles. So mass and moles, this is the mass and that's the moles. So that's the conversion factor number 1. This equation will give this conversion factor, and the next conversion factor is between moles and number. So that's the moles and number. So therefore this equation will give us conversion factor number 2 here. So let's plug in the values. So first is the mass of ibuprofen, it should be in grams. So we already calculated is 0.200 grams of ibuprofen multiplied by first conversion factor. So now the given value grams is on top, so in conversion factor it should be in the denominator, so it means 194. So that's where I'm getting my conversion factor, right? So 194 grams should be in the denominator because we want to cancel grams. Grams of ibuprofen, and on top will be 1 mole ibuprofen. So now grams ibuprofen cancels with grams, and we have left with moles now. So multiplied by the next conversion factor. So next conversion factor is between moles and number of molecules. So moles are on top, so therefore here we will write 1 mole ibuprofen down here, and on top will be 6.02 times 10 to the 23 molecules. So let's cancel moles with moles, and let's clean up this equation. So this will be equal to 0.200 multiplied by 1 multiplied by 6.02 times 10 to the 23 molecules divided by 194 times 1. And when we solve this equation, the answer will be equals to 6.2 multiplied by 10 to the 20 molecules of ibuprofen.